we will start now with the first paper, which is the paper from Mr. Yulius Wibisono, Pak Anto Satriyo Nugroho, and Pak Maulahikmah Galinium. So, and the title of the paper is Optimization on Malaria Computer-Aided Diagnosis System. So, okay, so I will now give the opportunity for, I think, Pak Julius, perhaps, to present the paper. Please, Pak.
Hey, thank you, Mr. Eka, for giving me the opportunity. Can we see the presentation now?
Yes, Pak.
Okay, thank you. Good morning, everyone. Now I'm going to present you our work that is titled Optimization on Malaria Computer-Aided Diagnostic with Mr. Anto Satriyo Nugroho as my advisor and Mr. Maulahikmah Galinium as my co-advisor. So in 2017, there are around 261,000 cases of malaria in Indonesia. And then to detect malaria presence, it can be done through microscopy on a thin blood smear. And manpower that can perform this ability is limited. And for a single case, for a single patient, a microscopist required 3 to 5 minutes to analyze a blood smear. Taking a photo of the blood does not require high amounts of resource. And this research has received grant from the Ministry of Research, Technology, and Higher Education of the Republic of Indonesia. Also, this research is also a collaboration between ICONETSI Institute of Molecular Microbiology and Agency for the Assessment and Application of Technology, or BPPT. This research is part of the roadmap for the development of the malaria computer-aided diagnostic, and currently is on the memory and computational complexity reduction to develop real-time detection chapter. So this is an example of a thin blood smear image, as you can see on the left side of the presentation. This is a single field of view that can be seen in, on average, around 200 field of view that can be seen on a thin blood smear. An example of a thin blood smear can be seen on the right side of the presentation, where it's located on the blood film, and then usually there are going to be 2 smears that is made, thick smear and thin smear, and the analysis is performed on the thin side. So the current existing problem is for a single microscopist to analyze a patient, it requires to see all the around 200 field of view in the thin blood smear. And for that, a microscopist requires 3 to 5 minutes to perform that. And the latest computer-aided diagnostic that was last developed by Winarta in 2017 can analyze a single field of view for 41.4 seconds on average. The problem is if we want to analyze a single patient, that means there are around 200 images that should be analyzed, and 200 times 41 seconds is not a really good time for analysis. So the purpose of this research is to look for the best algorithm configuration to achieve minimum runtime. Our target is real time. There is around 1 second per image. So the methods that is used in this research is, first we prepare data, and then we perform benchmarking on the existing computer-aided diagnostic, and then we perform analysis on the code of the computer-aided diagnostic, and then we propose algorithms. After that, we develop a prototype code, and then we perform a runtime experiment to see the increase in the runtime. And then while we're at it, we are also will also do an experiment on the accuracy to see whether it is reducing the accuracy or not. And then the code will be applied if things are better. So the proposed algorithms are, there are 4 main algorithms that is proposed to replace the old program. That is component labeling with labeling box. So the labeling of foreground objects are only performed on the relevant space of the foreground object. This greatly reduces the array access count. And then the second is contour tracing labeling without inner contour extraction. So rather than performing connected component labeling with dilation, with opening, we perform it with contour detection and then filling the contours that is generated from the foreground object. With this algorithm, we hit two birds with one stone, that we also perform hole filling. Also, the other algorithm is we perform downscale before we perform clump splitting, so that amount of element that have to be accessed when performing this algorithm is reduced by to a quarter of the original resolution. And then concave point-based clump splitting performs clump splitting only on the possible points that a clump should happen. That is a concave point. So, and you see the comparison between the connected component labeling algorithm. The contour tracing labeling without inner contour extraction have the most improvement, as it also reduces the computational complexity from the big O notation of n squared to only n. And then the element size also greatly reduced, because the element that is need to be accessed is only the pixel count of the foreground component. And other than component shape extraction, this algorithm also performs hole filling at the same time. For the clump splitting algorithm, the concave point-based clump splitting still has the same computational complexity, but it have a greatly reduced element size. That is only the count of the concave points of the foreground object. So for the result, this is the program flow of the original program, as you can see. The algorithm that causes the most runtime is the connected component lab, is the hole filling part, and then the connected component labeling part, and then the clump splitting part. And then after the clump splitting is performed, another connected component labeling will be performed again, so that will take a toll on the runtime. So this is the runtime after the optimization is performed. We can see the original program on average have 41.458 41.458 seconds on average per image. And then we can see that the program after optimization is being performed on average requires only 1.73 seconds to analyze in an image. For the accuracy result of the healthy versus infected classifier, we can see an improvement on the accuracy, because the program stability is also increased. We can see that the precision value is raised and the F1 value is raised on the optimized CAD. And then for the species and life phase classification, we can see that the accuracy for the Plasmodia species classification is increased on the optimized computer-aided diagnostic. But on the life phase classification, it is actually a little bit reduced. But also the reduction is also being caused by the amount of data set that is different, because the optimized computer-aided diagnostic is able to analyze more images without crashing. So the conclusion of this research is that this study has successfully improved the computer-aided diagnostic from a runtime of 41 seconds to, sorry, I think this is a typo, to 1.73 seconds on average. That is 22.95 times faster. And then the optimization also increased the stability of the program. And then this study has contributed of the finding to the hole filling zip contour tracing labeling without inner contour detection and concave point-based clump splitting. And this study has also moved this project a step forward so that the malaria computer-aided diagnostic may be prepared to be used in the field. Thank you for your kind attention.
Thank you very much, Pak Yulius, for your presentation. So I will now open the question and answer session. So we have around 10 minutes time for this. So if you have any questions, please write it in the chat. Okay. While waiting, I have a question, Pak Yulius.
Yes.
So I mean, your result is quite impressive. It is an increase of 22 times faster, more or less. So, in your opinion, Pak, what is the main contribution for this increase in the speed?
So the main contribution is that the previous algorithm requires the scanning of all pixels in the image to extract the foreground objects. And then the algorithm use having a big O notation of n squared. That means it's going to be taking a long time. But after the optimization I've performed, some of the algorithms is replaced with a better version of it that only requires that have the computational complexity of big O notation n. And then the amount of element in the problem is greatly reduced to only the pixels, the amount of pixels of the foreground object. So we can see, we can think it as if before we have to scan the whole image to detect one cell for each cell, now we only have to scan the amount of pixel of a cell for a cell. I hope that's clear.
Okay. But to detect the cell, does it not need another computation, Pak?
So when
to detect the cell that you are interested in, I mean.
Yeah, that will be the computation will be performed later after all the cells have been labeled first. So first we have to recognize if the cell is really a cell. Yeah.
Yeah, that is also a problem, yeah.
Yeah.
Whether it is a cell or just something else.
Yeah, that's true.
Okay, but this speed up that you mentioned, does it already taken into account all this pre-processing part, Pak?
The pre-processing part is mostly the optimization. The optimization process is actually done most in the pre-processing part.
Oh, okay. So this speed up has already taken into account that we have to find the cell and then we have to identify whether it is a cell or not. It is already taken into account, yeah?
Yes.
Okay. Now I have another question, Pak Yulius. This is Bu Patricia. So the question is, what do you think the accuracy? What do you think the accuracy is the detection? So I think the question is asking you to give comments about whether the accuracy of detection is actually meeting the need, the real case need. Is it already enough that accuracy, or is it does it still to be improved?
Okay, so another further study is actually required to test the application with a much larger data sets, and this must be performed to determine exactly this because currently we do not have information whether this is what possible for real life use yet or not, or another iteration of programming required for this converted diagnostic. Does that answer the question?
Oh, okay. So do you mean that in real life, so in real clinical practice, let's say, CAD is not yet used, Pak?
Not yet. As far as I know, it's not yet used.
Okay, so it is always manually done. Is it like that?
Yeah, in remote areas for now, it's like that.
Oh, okay. Yeah. So, okay, but if it is done in the laboratories, let's say, yeah, manually, what is usually the current accuracy, Pak? Do you know?
No, I don't have the information to.
You don't have the
answer
information.
That, yeah.
Okay. So, yeah. Do we have other questions? Okay. Oh yeah, Pak. I want to ask you something. You mentioned something about the labeling of the cells, Pak. Who is going to do the labeling?
I'm sorry?
you mentioned about labeling of the cells,
Yes.
whether it is malaria cells or not, I think.
Yes.
So who will do this labeling, Pak?
It's the application. It's the program, of course. The labeling here means that the program can successfully recognize if cell A is different cell from cell B. So labeling means the program can label the cells. Cell 1, cell 2, cell 3, cell 4.
Okay, what kind of features is used to actually recognize whether a cell is actually a malaria infected cell or not?
So there are more than one, of course. There is the circularity, there is the area of the cell, the size, and the color is also as a feature. The ratio, the aspect ratio of the cell is also calculated to
okay,
to recognize whether it's infected or not. And also we try to extract the shape inside the cell also. So for example, we can see, maybe we can see here. Is it clear? Is it?
I can see it.
Okay, so can you see my mouse?
Yes.
Okay, so in here we can see that the cell have a little spots inside. This usually indicates the presence of plasmodium. That means we are trying to also extract the shape of the plasmodium inside the cell to determine what species the infection is and what is the life phase of the plasmodium that is residing inside the cell.
Okay.
Yeah.
So these features are also the features which are used by the laboratory technicians, let's say?
Yes, of course.
The same thing.
Yes, the same thing.
Okay. So I have another question from Mr. Aan Kasman here. So the question is, would you consider cloud computation resource in order to test and verify your model as the data are mostly images?
Yes, that is actually considerable as a higher computational power and more data definitely will help to this research.
Okay, but cloud computation is, do you think it is an option, Pak?
I think yes, I think it is possible. Because in remote areas, the computers are not that good yet, right? So a cloud computation server will be definitely helpful for a real life case.
Okay.
I hope that answers the question.
Yeah. But yeah. So, but I mean here, Pak, your main there is a constraint of the speed of the testing, isn't it?
I don't quite get the question.
Yeah, I mean you said, I think in your conclusion that the design requirement is actually 1.5 seconds per image.
Yeah. One seconds per image. The desired
1 seconds per image. Yeah,
yes.
There's a constraint for the speed of the testing, isn't it? But do you think if we apply cloud computations, considering that the connection in Indonesia perhaps is not very good or everywhere, as I can say, do you think it still makes sense, Pak?
I think it would still make sense, but the most time taken will be on the transmission of the image rather than the computation if we use cloud computation. But
okay,
it would actually improve the analysis time, I guess.
Okay, good. So thank you very much, Pak Yulius, for your answers. So due to the time, I think we have to move on, Pak. Thank you very much, for your presentation.